Okay, let's start this section, calculating volume. Okay, um, so as you would expect, volume is a good candidate to treat as a Riemann sum. We can clearly add volumes. The only trick to doing a Riemann sum is how do we think of it as a product of two things? Because usually we think of volume as three-dimensional. Well, think of a solid with a constant cross-section. Then the volume will be that constant cross-section area times the height. And so, for example, here I've got, like different kinds of cylinders. You think like a rectangular cylinder, which is kind of like a box, a normal cylinder, and it looks kind of like a L-shaped cylinder, an L-shaped base. So if each of these solids has constant cross-section of 3 square inches and has a height of 2 inches, how much volume is in each object? Okay, that should be very straightforward. The trickier problem is, what if our cross-section areas keep changing? And the answer is, well, we do a Riemann sum. So, estimating volume. So here I've got some amorphous blob out there. Let's say we can find the cross sections of this blob at 1 inch intervals and say, we see there's 7, 10, 20, 30, 25, 21 square inches as we go. Then, so what's that? That's 6. So we've cut up our interval into 6 sub-intervals. So we're estimating our solid as 7 cylinders. And so then we just add up those volumes. And so it's 1, because that's the height of each of the 6 sub-cylinders. And then 7 plus 10 plus 20 plus 30 plus 25 plus 21 is 113 times 1. So we estimate that volume to be around 113 cubic inches. And of course, to get a better estimate, all we've got to do is take a finer subdivision. Okay, so all these things looking kind of the same. So we have that our volume of our solid is going to be the Riemann sum of the area. So the volume is going to be approximated by the sum of the area of the cross sections times the heights of the little cylinders that we're taking. Okay, so let's look at our standard example. So, we've been looking at circles and discs and that, so let's look at spheres. Because we know what the answer is, right? Because the volume of a sphere is 4/3 pi r cubed. So let's look at a sphere of radius 1. So that has volume 4/3 of pi, which is around 4.188. So if you look on the far left there, I did 5 equal sub-intervals. So the radius of 1, so I'm thinking of my cross sections of going from -1 to 1. Okay, so I cut it up into 5 equal sub-intervals, so I got -1 to -0.6. The midpoint of that is -0.8. Then I've got -0.6 to -0.2. The midpoint of that is -0.4. -0.2 to 0.2, the midpoint is 0, etc. So that's my 5 midpoints that I'm doing. The formula for the radius then is going to be square root of 1 minus x squared, because we've got a circle sort of like covering things. So the area of the cross section is pi r squared. So if the radius is square root of 1 minus x squared, the area of the cross section is pi times 1 minus x squared. So there's our approximation. Okay, so get 1 minus -1 divided by 5. So 2/5 is kind of the height of each of our cylinders. And we want to have pi r squared. So we've got minus 0.8 squared equals 0.8 squared, and minus 0.4 squared equals 0.4 squared. So that's why I've got those two. So I've got 2 pi times 1 minus 0.8 squared plus 2 pi 1 minus 0.4 squared plus pi times 1 minus 0 squared. Okay, so that is 1.36 pi. That's pretty good. That's pretty close to 4/3 pi. It's only an error around 2%. So to get a better answer, we're going to use the Excel file Riemann using the function pi times 1 minus x squared on that interval -1 to 1. Okay, so here is that Riemann file. So again, so here I've done 32 subintervals. So I'm going from -1 to 1, and here's the points of my grid, and here I'm just taking midpoints because that just gives us more accurate answers. And so the volume is pi r squared, right? So that's pi times 1 minus x squared times the height of the thing. So that gives a volume. So it's kind of like we're adding up all kind of little disks. And so if we go through and do it for 32, we get 4.19. Okay, and so if we look at what 4/3 pi is, it's 4.188. Okay, so we've got like a 10 times better estimate by doing this. And of course, if we wanted to do even a better one, so let's say we want to do, I don't know, 256. That's just a finer. So I go through and copy and paste. Whoops. 256. 256 is 1 point. So let's compare that to 4/3 pi r cubed. It's pi 8879, and then we've got 1.8. And so we see we're getting really good answers here. Okay, so that's what we've been seeing all semester. Okay, so we see, again, this is just a good way that we can actually figure out volumes. And so last slide, this is the second module question. It's a little bit more complicated than one that I usually give you. So here we have a light bulb, and I want you to estimate the volume of the light bulb. So we think of the cross sections as being circles, and so the numbers that are given there are the diameters. And there's one diameter missing right at the top there, because there it's 0 centimeters. And 5 centimeters is the height of the light bulb. So we see that we've cut up the light bulb into 10 discs, okay? And so the volume is going to be, right, it's 5 divided by 10, 5 centimeters divided into 10, so it's half a centimeter each disc, and it's going to be pi r squared. And so you've got to halve those diameters there, and it's like for the first disc, it's somewhere between 0 and 2. If you use 2, it's going to be too much. If you use 0, it's too little. So you've got to think of some way to do it and come up with an estimate for that. And that finishes this module. Okay, see you on Wednesday.